Hello participants, I invite you to lecture 56 of micro irrigation engineering subject. Lecture 56 is on economic analysis of micro irrigation system part 2. On the same topic part 1, in lecture 54 we discussed about different terminologies which are important for economic evaluation, where different types of cost terms it comes, benefit cost analysis, net present worth, how to compute. So, different expressions which are involved to estimate we discussed in previous lecture. In this lecture we are going to discuss on the critical flow criteria, how for selection of micro irrigation pipes. We will be dealing with optimal flow, and then this concept has been utilized for an hypothetical example, considering a hypothetical example for a 6 hectare area, in order to make you understand how optimal flow criteria can be used to select the particular size of pipeline. In theoretical consideration, before I speak about different terms involved, let us try to first revise the terms which we discussed in the design part. In design, we estimated head loss due to friction. Our aim was to reduce the head loss due to friction. So, we are considering the size of the pipeline in such a way, whether it is a main pipeline of micro irrigation system, whether it is a sub main pipeline of micro irrigation system, or it is a lateral pipeline. So, our aim was to reduce the head loss due to friction and other losses which takes place in the pipeline. So, if we are considering say one particular pipe size and we find that head loss due to friction is some quantity in meter, and then we are taking another which is higher than the previous one. So, question comes, what should be the size of the pipeline one should select. So, one always feels that yes, if I am going for the larger size, then economics come into picture, that whether we are taking a new higher size pipeline, then economics is important. Now, if we are considering this shorter pipeline, means head loss due to friction will increase, but it is in the permissible level, but the amount of energy required, because that is a variable cost, it will continue to every time when you are operating, the variable cost will increase. So, that is a cost which will be recurring almost daily as and when we operate the pump. So, these two costs which are there, one is due to the size of the pipeline, another cost is due to operational, that is a variable cost. So, operational cost. So, these two things are to be considered, which size of what size of the pipeline should be considered. So, the term which has come, it is a life cycle costing technique. It has been used to optimize the pipe diameter to determine the optimal flow between two pipe sizes. Two adjacent pipe sizes are two pipe sizes which are just one is say 12 millimeter, another one is 16 millimeter for the case of lateral. So, whether should I go for 12 millimeter, I should go for 16 millimeter, that is the two adjacent pipe means. Now, when we talk of the economic the optimization part, we need to consider several factors, that is the size, market price, and then what is the applicable rate, and then how many hours the system in a year the pump will operate, and then what is the overall efficiency of the system. All these things will come. The important term here it will be used in all throughout my presentation is optimal flow. What is this optimal flow? It is the flow rate at which the total annual cost between two adjacent pipes can be equated. Means we are equating these two pipes and then seeing that whether which pipeline will be giving best flow rate which will be useful for us. So, these two pipeline values they will be used, and then in order to find out the optimal flow between the two diameters. Now, if we are considering, let us say D1 and D2 are the two pipe sizes and their respective cost per unit length is given as a C1, C2, that these terms we will use in further, but let us come to the what is the capital recovery factor. This is a common terminology when we are making the estimation. So, capital recovery factor, it is a function of prevailing interest rate in a given period of time. So, this can be given by the interest rate plus into 1 plus interest rate to the power number of years or number of months, whatever we take, that is n is the period, and divided by 1 plus I to the power n minus 1. So, n is the number of life period, number of years, and then I is the interest rate in percentage. When we are talking about the total cost to estimate, we are interested about the finding out the critical flow. So, critical flow criteria means we will be equating these two terms, that is one total cost is the annual cost of the pipe and annual cost of pumping. One it is written to this refers to the diameter D1. Now, similarly for other diameter D2 TAC2 can be computed. Now, as I told you that according to this criteria, the means these two costs, one is the cost of the pump pipe and of the diameter D1 and cost of pumping by using the pipe diameter A1 is equated with the cost of the pipe, annual cost of the pipe having diameter D2, and then corresponding what is the annual cost of pumping for the diameter D2. So, these are equated. Now, this annual cost is put up in the form of fixed cost and operating cost. This C means the term in the subscript 1 refers to the diameter D1 and subscript 2 refers to the diameter D2. So, FC1, FC2 these are the fixed cost and operating cost. Now, this can be given that means fixed cost and your operating cost, it is brought in terms of the horsepower requirement multiplied by the cost of the this is the cost of water horsepower. So, this part when operating cost it is brought in terms of the economics value. So, this can be given as a means this is a standard formula, the horsepower, what horsepower can be computed by this one, that is the flow rate multiplied by the head. So, this H1 and H2 these are the head losses or head, we can say total head of the pipeline D1 and the diameters are D1 and D2, and this is just simply discharge of the unit, that is the your flow into the system, and then this is a unit constant, that liter, it is given in the liter per hour. So, this way we are putting it equating this part, and then the cost of the horsepower is given by the energy cost multiplied by the horsepower, operating horsepower per unit, means in a year how many hours in a year the pump will operate divided by the pumping efficiency. So, when we are this particular equation, equation 5 is written in this form. This can be written as a means the flow rate divided by the 75 into 3600, it is in liter per second. This is the difference, means we are equating this part. So, this has come as H 1 minus H 2 multiplied by the cost of the water horsepower is equal to the difference in annual fixed cost. Okay, difference in the annual fixed cost means when we are considering D 1 and D 2. So, this way we are getting the expression. What is the means expression we can get in terms of H 1 minus H 2, that is the head loss when we are considering two diameters in terms of the cost unit. Now, this particular equation which we have got equation 2, this means this is a head loss. So, head loss is equated, that is HF. HF is equated by using the appropriate friction factor depending on the type of a flow regime. Now, this H 1 and H 2, that difference is written in the modified form of the Darcy-Weisbach equation. We already discussed this particular pipe when we were discussing about flow through pipes. So, Darcy-Weisbach equation as well as Harogen-Williams equation we have discussed in previous, and then if you remember, this simply Darcy-Weisbach equation is H f equal to F L V square by 2 G D. So, that V square term is brought in terms of the means Q square by A square, and A square can be written as pi D square by 4. So, this is the modified form of that component. It has been brought from the means equation, and that equation it is in this form it is written. Now, that H f is it is substituted in this then there is a equation which we will use for finding out this F. This is a frictional factor F will be substituted by using the appropriate equation for the Reynolds number. So, let me just show you that Reynolds number is given by the 4 Q divided by this K. K is a constant, that is equal to 3600, because this unit is here liter per hour, and this eta is the this kinematic viscosity, and D the diameter of pipeline. So, this way it is given, and then here we know if the flow is in the turbulent range. So, flow is in the turbulent range means fully turbulent range when we are talking. So, Reynolds number is between 4000 to 10,000. So, this particular component we are going to introduce. So, for turbulent flow condition we are putting the appropriate value for the in the equation 8 we are so equation 9, 10 and 11 is substituted in equation 8. So, what is that equation 8? I am just bringing you back. This is this was the equation 8 where we have. So, this is H f practically. So, this we are putting H f in terms of the Darcy-Weisbach equation. So, this equation we are putting it, and then we have substituted the 10 and 11 by substituting the appropriate value of the Reynolds number, and equation comes in this form. So, here again you are equating by considering the two diameters, that is the diameter D 1 and D 2, and then the equation it can be written that this particular component can be given by the D f into 75 3600 Q. So, from there actually this equation it has come from equation 8. Now, assuming that the flow through the unit is equal to Q u equal to Q c, that the flow through the system equal to critical flow. The equation above this, that particular equation 12 can be converted in the this particular form for calculating the optimal flow, between the adjacent diameter, that is d 1 and d 2. Adjacent diameter, as I told you, that what is the next diameter, if not the previous diameter, what is the next diameter. So, normally say when we are considering the main pipeline, so 63 millimeter is the internal, let us say 63 millimeter is the internal diameter of the pipeline. So, next available diameter is 75 millimeter. So, comparison is made between the next adjacent diameter or 75 millimeter is nothing but 3-inch pipe size. So, it can be 3-inch pipe size or it can be 3.5 inch, that is 90 millimeter. So, like this we are using different. So, QC is converted in this form by using the equation 12, and where it is coming in the form of the ratio of K 1 by K 2 and then 1 minus d 1 to the power 4.75 minus 1 by d to the power 4.75, where K 1 is this expression. K 1 is to be obtained by using this expression, and for a given set of condition K 2 becomes 0.65465. So, optimal flow between two adjacent pipe diameter can be obtained by using the data on available pipe sizes which are available in the market, their cost, applicable bank interest rate, cost of the energy, hours of operation per year, and overall pumping efficiency. So, this way it can be used in finding out the optimal flow. So, the equation 13 can be written in a generalized form, that is your optimal flow rate QC can be given by this expression, and where if means there are two cases it has been considered. This is a generalized form of the equation, where if I am using say Darcy-Weisbach equation, Darcy-Weisbach equation, it has a provision to estimate friction factor F when the flow is laminar, transitional as well as for turbulent flow, whereas Hagen-Williams equation it is used only for a specific case, means there is the value of F, there is no provision to change. So, normally this is for turbulent flow case. Now, here the value of K 2 is estimated when F is taken as for laminar flow case. So, K 2 is obtained from using the previous expression, and then corresponding A and B which is there in the expression, those corresponding values of A, here A is the exponent here, and then B is obtained for different F values and as well as for the C equal to 150. So, having got this value, we can develop a curve that I will discuss. So, optimal flows in drip diameter, where it requires means the information related to two adjacent pipe sizes, annual interest rate, how many means the number of hours, operating hours in a year, then what is the life of the pump pipes, that is what some for PVC pipeline and plastic pipeline, normally it is a 40 years it is taken, and overall pumping efficiency as well as energy cost. So, if it is a main pipeline, it is a 25 to 40 years, normally 25 years people take, but maximum it is given, as I was telling that Thomson table in the previous class, which I told you that when we were estimating the depreciation. So, there it was considered as a 40 years, but 25 years is the period it can be taken, and then number of operating hours in a year. So, this way it is calculated. Now, life period of pipes vary based on the pipe material, hence suitable value for the life period is considered that what is the type of pipe material which we are using in the analysis. Now, details of the pipe sizes and then the unit cost is, of course, these costs which are available, these costs are very old, pretty old, means it considered based on the price which were prevailing price of 2006. So, by Dr. Ella Reddy, he did it in his PhD research work. So, same data, he did PhD research work at IIT Kharagpur in the Department of Agriculture and Food Engineering with me. So, same data which I am producing here in the year 2006, and same data it has been used here. So, given these data and the pipe sizes, the critical flow values which were obtained, and then a graph is plotted when we are considering the life period. Of course, in this particular case we are considering 10 years, and then the annual operating hours is 2000 hours, annual interest rate, a general interest rate it is taken as 12%, pumping efficiency 65%, and cost of energy is 1 rupee per BHP hours. So, when it is a plot, you can see here how it is plotted, then it is plotted for different successive pipeline, and then the critical flow rate. So, one is this particular thing, means this particular curve, when it is plotted, it is a coinciding when we are considering the turbulent flow case, means we have taken a turbulent flow case, means and this turbulent flow case, what we find that the Hazen-Williams equation as well as the Darcy-Weisbach equation, it is giving the same the values, means they are not same value, but almost it is coinciding. So, optimal flow range were obtained by considering the successive pipes under turbulent flow and fully turbulent range for the Darcy-Weisbach equation and also with the Hazen-Williams equation, when we are considering the constant C for the pipeline is 150. So, when we consider the Darcy-Weisbach equation for the turbulent flow, optimal flow for the pipe size combination of 40 to 50 millimeter is it is we are getting the flow rate as 5085 liter per hour, and when we consider say larger size pipeline, it is 75 to 90, we are getting 21,049 liter per hour. Now, these values indicate the flow rate at which the pipe has to be, means one can means the flow rates at which the pipe sizes can be changed. For example, when we are taking it, the flow rate is accepted, it is between it means the pipeline is between 13,500 to this range, then 75 millimeter pipe size is advisable. Now, when the flow rate it exceeds 21,449 liter per hour, then one should use the 90 millimeter pipe size. So, in this range a smaller pipeline can be taken, but when it exceeds the value, then the higher size is recommended when we are considering the optimal flow criteria. So, optimal flow criteria provides a useful information for selecting the pipe size of the pressurized irrigation system. Now, in order to use this economic means this particular criteria, so a hypothetical example has been taken where the drip system has been considered for 6 hectare banana crop, and then the data which has been used for this study, it is a spacing is considered as a 2 meter by 2 meter, and this 6 hectare area it has a the length of 400 meter and then width of 150 meter. It is a flat terrain. We have considered it is a the medium textured sandy loam soil, and then the peak evapotranspiration rate is 9.75 millimeter per day, and then the well is, of course, this is a considerably very high value. Normally this evaporation rate in our country it is rare, but it is a hypothetical question that were to make you understand about this particular thing. So, this is not exactly it is happening in our case. Normally in our country the evaporation rate it is varying from maximum it goes up to 6 to 7 millimeter per day, and well it is a source of means well it is taken as a groundwater and static water level is 8 meter. Emission uniformity is considered as a 90%, and then the there is a limiting velocity. This is the value where maximum velocity it is recommended by American Society of Agriculture Engineers, that in the pipe flow, particularly for drip irrigation pipeline, the velocity should not exceed more than 1.5 meter per second. The other cases here you can see here we have taken the lateral pipeline, sub main pipeline, main pipeline of these sizes, and then their corresponding. So, lateral pipeline it is given as a DL 10, DL 12, DL 60. DL means diameter of lateral pipeline of 10 millimeter, 12 millimeter, 16 millimeter. Though cost it is less now, this prevailing cost at present means these are the costs which were assumed means this were taken 15 years back. So, these costs are considerably very low, but it will go high. Then in case of sub main pipeline, the pipe sizes were the 50 millimeter, 40 millimeter, then 50 millimeter, 63 millimeter, and main pipeline it is it has been taken 75 and 90 millimeter. And then as I told you that this is the field size of 400 meter 400 meter by 150 millimeter, which is 6 hectare area, and there is one dripper of 4 liter per capacity to each plant it has been given, and these are other information that total number of plant for the 6 hectare area is 14,800, and then one row it is kept it in the middle, so that easy operation for the operation of the sub unit can be made. Means suppose it is a manually operated system, then one has to go and operate the valve, etc. Now, considering the all the 14,800 plants and 4 liters of water per hour. So, the discharge requirement is 59,200 liter per hour, and then the it is also considered that the flow in the main pipeline, when we are considering this discharge, the flow velocity it is coming 2.59 meter per second, which is higher than the required. So, we need to consider such velocity which is in the as given in the suggested by American Society of Agricultural Engineer, and from the from the market available, these are the sizes it has been considered. And in order to not to operate the all the lines, lateral lines, so there are the arrangement it has been made that it can be considered 2. So, means there are 2 irrigation plan it has been suggested. So, half of the field it will be, so it is there. So, you can see here the layout it has been made. So, here layout it goes like this. This is the source of water, and from the source of water there is a pump, and pump is connected with the main pipeline. So, pipeline goes from the middle of the field, and then these are sub main unit, and then with these sub main units the lateral pipelines are attached. Total you can see here there are total 8 sub units. Means there are total 8 plots or 8 sub units. So, 1, 2, 3, 4 on this side, and then 5, 6, 7 are on this side, and this particular sub main which is there, it is supplying water to the up to this part. So, there will be here valve, it will be closed when we are going to apply water to the subunit this particular plot 5, or we will be again having. So, all these subunits are given valves to operate on. So, this is the arrangement we can, the other details are available in the problem. Now, as there are two irrigation plan which has been suggested. One irrigation plan that irrigating subunits 1, 2, 3, 4 in one shift, 1, 2, 3, 4 in one shift. So, from here this is the middle part, and then the these are the 4 subunits are being irrigated, and then 5, 6, 7, 8 is another shift like this. There are two. The another one is giving irrigation to 1, 2, 7, 8 means this part, and 3, 4, 5, 6 in the another shift. So, there are two arrangement, and optimal flow rates are computed for successive pipes, and then here these are the data which has been considered, that is the life period is 10 years, interest rate 12%, and these are the other data which already I have told you. So, in order to study the effect of time of operation on optimal flow, the analysis has been made by considering the time of operation in a year, that is 500 to 2500 by taking the interval of 500 hours. So, here we can see here that these are the operating hours, and when we are considering the optimal flows estimated are given in the table, where this indicate the flow rate at which the pipe diameters can be changed from lower to higher for the consequent pipe size of 63 millimeter to 75 millimeter and 75 to 90 millimeter. So, this way we are getting the values, and then these values are optimal at which the optimal flows are obtained. So, what we are say, let us say that it is the when we are considering the 2000 hours of operation, the pipe size required to be changed from 63 millimeter to 75 millimeter when flow in the network exceeds 13,520 liter per hour. Similarly, the pipe size has to be changed from 75 to 90 millimeter, means particularly at the flow rate when it exceeds 21,048 liter per hour. Here this has been converted to liter per second, means liter per hour is converted to liter per second. So, design of main pipeline when means this is another criteria that was for the optimal flow criteria, and when we are making the velocity as the criteria. So, when we means the limiting velocity is taken as 1.5 meter per second as per the recommendation of ASAE. So, flow velocity is in the main pipeline for different flow rates. So, when we are considering 63 millimeter pipe size, so we will find out the area under this pipeline, and then when we have got different expected flow rate. So, we will get different velocities for the different sizes of the pipeline. 63 millimeter pipeline. So, this we are getting 0.66 meter per second, and then when we go for the higher flow rate, the velocity it comes to this one. Now, when we go for the further higher flow rate, we find that 63 millimeter pipeline will be exceeding the velocity limit of 1.5 meter per second. Then one should think of if the another the another pipe size, that should be the higher pipe size line. Similarly, for the other pipe lines, then so these are the values one can select by considering the velocity criteria. So, in calculating the pipe sizes for the maximum flow expected to each zone has been calculated. We are assuming means there are some other assumption which is given, that the length of pipeline when we are connecting with the source of power is 10 meter, and the two irrigation plant which I have already discussed you how these to be operated in shift 1 and shift 2. And when we are using the irrigation plant say 1, the requirement of the pipe where 100 meter pipe of 63 millimeter, then 100 meter pipe size of 75 millimeter, 110 meter of the 90 millimeter pipe size, means considering when we are using the optimal flow criteria. And with irrigation plant 2 when we are considering, so these are the dimensions which we are getting for the 2 pipe means your other plant. So, the estimates were also based on the taking the each segment. Now, estimates are made for the irrigation plant assuming 3, 4, 5, 6 subunits are to be irrigated in one shift. So, the segment of pipe carrying water to the subunit 4, 5 should carry this much amount of flow, that is 14,800 liter, and should be of this diameter, mean 100 meter long pipeline of 75 millimeter. In the then the entire area for 3, 4, 5, 6 these are the pipeline which has been suggested based on the optimal flow criteria when we are using, and accordingly the cost were estimated, and then what we find the cost of the main pipeline when we are using I1 plan and I1 plan, I2 plan, what we find that the there is a net saving in the rupees of 2,770 by adopting using the plan I1 as over I2. So, I1 is more successful when we are taking the optimal flow criteria. Now, this indicates the selection of irrigation pipe is an important aspect to optimize the pipe requirement. Then the estimates which has been made for the different length of the pipeline on the basis of optimal flow criteria and velocity criteria. We have taken both the criteria when we are comparing. So, what we find that the this is the combination when we are using for 63 millimeter pipeline of 100 meter, 75 millimeter of 100 meter, 90 mil. So, this way, so total cost it comes to 1242, whereas velocity criteria it is giving 900 282 when for the irrigation plan 1. Similarly, in case of irrigation plan 2, the total cost come to 14,000, and in this case it is coming 13,722 rupees. So, this way one can compare. So, comparison is made taking the different pipe sizes and also by using the two different criteria, that is optimal flow criteria and velocity flow criteria. So, maximum velocity criteria. So, what we are finding that the frictional head loss in the main pipeline is taken estimated by considering the total flow which is taking place in each zone. Annual cost of the main line was more for the larger pipe size, and however, the annual operating cost it becomes less because the frictional cost or energy requirement is less. So, total annual cost considered for the purpose of comparison, the pipe size combination with the lower annual cost are better for selection. In all irrigation plants, the optimal flow criteria proves to be more economical. Now, in calculating the head horsepower requirement, constant of 2 meter of head in accessories and 8 meter in means the 8 meter for the suction head which is given in the question, that has been added, and then we are concluding we are taking the 10 meter at the pressure head to operate the drippers, and total head requirement estimated to be 20 minus these losses plus frictional losses in the main pipeline. So, in all the cases optimal flow criteria proves to be requiring less horsepower to operate prime mover than uniform size of 63 and 75 millimeter size. So, use of uniform size of D90 would need less prime mover size, but annual cost of the pipe would be much higher than those selected with optimal flow criteria. So, this shows that optimal flow criteria should be the basis for pipe selection in selection of main line in drip irrigation system design. So, this is the comparison which I have told you, that optimal, when we are considering the optimal flow criteria, the energy cost and then annual fixed cost, the horsepower requirement of the prime mover. So, this is all it is lesser than the velocity flow velocity criteria when we are taking it. So, it is, you can see here, this is 29,961, where it is 2,961.5 rupees, where this comes to 2,999.5 rupees. So, like this here also you can see it is lesser than the velocity maximum velocity criteria. So, this is giving optimal result. So, let us summarize this part. The optimal flow criteria and life cycle costing technique have been used for the development of equation, for finding out the economical pipe size. The model equation developed was based on both economic as well as hydraulic consideration. It estimates the flow rate at which the designer should change from one size to the another pipe size. We have taken an example for implementing in 6 hectare area for the comparison purpose, and then we found that the annual cost was lowest when we are using the optimal flow criteria. In all the irrigation plant, optimal flow criteria was found to be economical. So, we this is the summary part which we do, and then in the forthcoming lecture we will again discuss about the economic analysis of micro irrigation system. That will be part 3 in continuation. You may refer these references, research paper which has been published in the journal, particularly on this aspect. So, you may refer this paper, and then also you can refer internet for this purpose. Thank you very much.